Chapter 10, Crustal Deformation. Structural Geology. Structural geologists study the architecture and process responsible for deforming of the Earth's crust. A working knowledge of rock structure is essential to our modern way of life. Deformation is a general term that refers to all changes in the original form and/or size of a rock body. Most crustal deformation occurs along plate margins. Deformation involves force, that which tends to put stationary objects in motion or changes the motion of moving objects. Stress, a force applied to a given area. There are types of stress. Compressional stress shortens a rock body. Tensional stress tends to elongate or pull apart a rock unit. Shear stress produces a motion similar to slippage that occurs between individual playing cards when the top card of a stack is moved relative to the bottom. Strain changes the shape or size of rock body caused by stress. How rocks deform. Rocks subjected to stress greater than their own strength begin to deform by folding, flowing, or fracturing. General characteristics of rock deformation. Elastic deformation, the rock returns to nearly its original size and shape when the stress is removed. Once the elastic limit or strength of the rock is surpassed, it either flows with ductile deformation or fractures with brittle deformation. Okay, so here we have some shortened compression stress. Okay, it tends to shorten a rock body. Tensional tends to lengthen a rock body. Shear distorts a rock body. Okay, so here with compression and brittle deformation, also there'll be a fracture, and one side will slip up and the other side will slip down. If there's enough pressure over time, you have ductile deformation and we end up with folds. Okay. Tension, enough tension, with brittle deformation, you'll end up with fractures where one block may slip down, the others may slip up, or it may cause extension or ductile flow, okay, which thins out the crust and the layers. Shear, with brittle deformation, you end up with a fracture, fault, and there's displacement along that fault, or you may end up with ductile flow, where you have permanent deformation. General characteristics, more general characteristics of rock deformation. Factors that influence the strength of a rock and how it will deform. Well, the temperature of the rock, the amount of confining pressure, the rock type, and how long it's under stress. Folds. During crustal deformation, rocks often bend into a series of wave-like undulations called folds. Kind of like you have a tablecloth on a table and you put your hand flat on the tablecloth and you push, and the tablecloth will sort of bunch up into folds. Characteristics of folds. Most folds result from compressional stresses that shorten and thicken the crust. Parts of a fold. Limbs refer to the two sides of a fold, and an axis is a line drawn down the points of the maximum curvature of each fold. Okay? The axial plane is an imaginary surface that divides a fold symmetrically, like a mirror. An anticline is the upfolded or arched rock layers. The syncline is the downfolds or troughs of the rock layers. Depending on their orientation, anticlines and synclines can be described as symmetrical, asymmetrical, recumbent or overturned, or plunging. Okay, so here we have an anticline. The fold is uplifted to arc. Okay, here's the axial plane that divides it in half. Each limb is the same size, same angle, so it's a symmetrical anticline. Okay, here the fold's starting to peter out. Okay, when you erode off the top, it looks like this anticline is plunging into the ground. Okay, it has kind of like this V shape to it. So here we have an anticline and then a syncline. These are symmetrical. But then this one is starting to be overturned a bit, so it's asymmetrical. As we have the axis here, this limb's longer than this limb. The syncline, and this one's overturned. It's been past 90 degrees. So we have this overturned limb, and here's the normal limb. Here's a syncline shown in rocks. And here's a plunging anticline in Wyoming. And if the picture was larger, you'd see over here is the plunging part of the syncline, and we'd have another probably anticline here. Another type of fold is a monocline. It's a large, step-like fold in an otherwise horizontal sedimentary strata. We also have domes and basins. Domes are upwarped displacements of rock, circular or slightly elongated structures. The oldest rocks are in the center, and the younger ones are on its flanks. First, there's a monocline, so these rocks were just bent still a little bit here. Kind of forms kind of like a step. So here's this monocline forming this step here. Here's a dome. The rocks are upwarped in a circular area, and then the top of this arc is this dome's been eroded away. So you see the oldest strata on the inside, and the younger strata is on the outside. Okay, here's another dome. This is in the Black Hills. So the center is granite, and we have a schist, okay, and other sedimentary layers out here, the younger layers. Basins are circular or slightly elongated structures as well. They're downwarped displacements of rocks. Youngest rocks are found near the center, and the oldest are in the flanks. So here we have our basin. It's kind of like a bowl, and when the top is eroded away, you have the younger stratas in the middle, and the older is in the outside. Here's Michigan Basin, Lake Michigan, Lake Huron. So here's another basin, and with erosion, the younger rocks are in the center, and the older are on the outside. Faults are fractures in rock along which appreciable displacement has taken place. Sudden movements along faults are the cause of most earthquakes. They're classified by their relative movement, which can be horizontal, vertical, or oblique. Types of faults. The dip-slip fault, movement is mainly parallel to the dip of the fault surface. It may produce long, low cliffs called fault scarps. Parts of a dip-slip fault include a hanging wall, the rock surface above the fault, and the foot walls, the rock surface below the fault. So here's a fault scarp here. Oh, actually here it is. He's standing down below, and here is top. So this little mini cliff here is a fault scarp. Here's our fault. The foot walls below the fault surface. You're the miner standing on the fault. And so the foot wall is named from a mining perspective. So here's a foot wall. And up above his head's a hanging wall. Okay. Normal faults. Okay, different types of dip-slip faults. Normal faults, the hanging wall moves down relative to the foot wall, accommodating lengthening or extension of the crust. Most are small displacements of 1 meter or so. Large-scale normal faults are associated with structures called fault block mountains. So here was our fault. Our hanging wall slid down, and our fault block has moved, or our foot wall has moved up. So here's some fault block mountains. So we have our normal faults. Okay, so where the rock has the foot walls have gone up, we have our horsts or the mountains, or also called range, and then between are our grabens or our valleys or our basins. How you look at where the head wall has slipped down. So this is a basin and range territory, or a horst and graben, fault block mountains. Reverse and thrust faults. A hanging wall block moves up relative to the foot wall. So it's the reverse of a normal. That's why it's called a reverse fault. Reverse faults have dips greater than 45 degrees, and thrust faults have dips less than 45 degrees. They accommodate a shortening of the crust, usually with strong compressional forces rather than tensional forces. Okay, so here we have our hanging walls pushed up, and the foot block drops down. Okay, dominant displacement is horizontal and parallel to the strike of the fault. Types of strike-slip faults. Okay, so this is a horizontal fault. Okay, we have a right lateral. As you face the fault, the opposite side of the fault moves to the right. If you face the fault and it moves to the left, it's a left lateral. So here's our strike-slip fault. Okay, and we're facing this way. This is a right lateral fault. And actually, we're standing this side and facing this way. It's still going to our right. There's a right lateral fault in Nevada. Transform faults are very large strike-slip faults. They cut through the lithosphere. They accommodate plate motion between two large crustal plates. San Andreas Fault in California is a good example. Actually, here's the San Andreas Fault system, and here's a picture of a portion of it. Okay, where one side is moving this way possibly, and the other side's moving this way, or it might be in reverse of that. Joints. Among the most common rock structures, technically is a joint. It's a fracture with no movement. Most occur in roughly parallel groups. Significance of joints is that chemical weathering tends to concentrate on long joints, so there's more surface area to work on. Many important mineral deposits are in place along joint systems. Highly jointed rocks represent a risk to construction projects. So here are some parallel joints in Arches National Park, Utah. Okay, mapping geologic structures. When conducting a study of a region, a geologist identifies and describes the dominant rock structures. Usually only a limited number of outcrops, sites where bedrock are exposed as surface, are available. So work is aided in advance in aerial photography, satellite imagery, and GPS. Describing and mapping the orientation or attitude of a rock layer or fault surface involves determining the features. So a strike is a trend. So it's the compass direction of the line produced by the intersection of an inclined rock layer or a fault with the horizontal plane, generally expressed in an angle relative to north. Dip is the inclination. It's the angle of inclination of the surface of the rock unit or fault measured from the horizontal plane. This includes both an inclination and a direction towards which the rock is inclined. So here is our line of strike. Okay, so and it's we talk about that in terms of degrees from north. And then here's our dip angle. It's our angle from the horizontal plane and the direction. So dip direction, it's dipping this way. Okay, and its dip angle is 30 degrees. The strike is 30 degrees from north. Okay, so here's our geologic map showing strike and dip of structures. Okay, so here, this part of the anticline, this sandstone here is dipping at 30 degrees in this direction. Okay, the trend here, the strike, is going this way. On this limb, so this is an asymmetrical anticline here. So this limb is dipping at 85 degrees in this direction. That's the end of that chapter.